Hi, this is Andrea Hendricks. I hope things are going well for you. Today's topic is higher degree polynomial functions and their graphs. In this video, we will talk about how to identify a polynomial function, identify the degree and the leading coefficient of a polynomial function, examine their graphs, describe the end behavior of a polynomial function, and identify key parts of the graph of a polynomial function. Let's first talk about what is a polynomial function. You actually have already worked with polynomial functions when we talked about linear functions and quadratic functions. Those are special cases of polynomials. Specifically, our polynomial function is something of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, right, a sub 1 x plus a sub 0. And you're probably freaking out right now looking at that notation, but just understand the a sub n is just a way to denote the coefficient that goes with the nth degree term. A sub n minus 1 is the coefficient of the next highest power. A sub 1 is a coefficient of the linear term, and a sub 0 is the constant term. And I'll show you how that goes through here. So whenever we talk about examples of polynomial functions, f of x equals 4x minus 2, that probably looks more familiar to you. In this case, n is just simply 1. And so all we're talking about here is a sub 1, which happens to be 4, and a sub 0, which happens to be the constant, which is negative 2. For f of x equals negative 2x squared plus 3x minus 1, our n is 2 in this case, and then we're talking about a sub 2, which is a coefficient of the square term, which would be negative 2. A sub 1 is a coefficient of the first degree term, which is 3. And a sub 0 is a constant term, which is negative 1. Okay? For 5x cubed minus 7x squared plus 3x plus 4, this is called a cubic function. Right? We have linear, quadratic, and cubic. For this case, n is 3, so a sub 3 is a coefficient of the cubed term, which is 5. A sub 2 is a coefficient of the square term, which is negative 7. A sub 1 is a coefficient of the linear term, which is 3. And a sub 0 is a constant, which is 4. We also have f of x equals 9x to the 4th plus 3x cubed minus 2x squared minus 8x plus 10. Well, here the highest power, or n, is 4. So a sub 4 is 9. A sub 3 is 3. A sub 2 is negative 2. A sub 1 is what? Negative 8, that's correct. And a sub 0 is 10. So when the degree or the highest power of this polynomial function is at 4, this is called a quartic equation. Now understand what n is, then n can be greater than or equal to 0. And really, in this case, n is just a whole number. Okay. Now the values of a sub I, I'll call them, can be any real number. I mean, you could actually talk about complex coefficients, but we're not going to get into that here. A sub I can be real numbers, so it could be fractions or decimals, irrational numbers, or anything like that. So hopefully, to get a more comforting feel to this, polynomial functions are really things you've already dealt with. Linear, quadratic, cubic, we talked about the basic cubic function, x cubed, so those are things that should be somewhat familiar to you. We're just going to expand it now to talk about any power of n. Now, the next objective is to identify the degree and the leading coefficient, because these are going to be very important when we talk about graphing a polynomial function. The degree of a polynomial function is just the highest power on the variable terms. The leading coefficient is the coefficient on the term with the highest power. So for these functions that we listed on the previous slide, let's talk about what the degree and leading coefficient would be. So the degree of 4x minus 2 is its highest power. Remember, x is understood to be to the first power, so the highest power is 1. The coefficient of that term is 4, which is the leading coefficient. What about for negative 2x squared plus 3x minus 1? The highest power is, the 2. And the leading coefficient is, the coefficient of that term, which is negative 2. For 5x cubed minus 7x squared plus 3x plus 4, the degree is 3, right? And its coefficient is 5, so that is the leading coefficient. For 9x to the 4th plus 3x cubed minus 2x squared minus 8x plus 10, the degree is the highest power, which is 4, and its coefficient is 9. Okay. Now some other things we need to think about are going to be whether or not the degree is even or odd, and whether or not the leading coefficient is positive or negative. So those are going to play a very important role when we talk about graphing. So just remember that odd numbers are like 1, 3, 5, even or 2, 4, 6, 8, so on. And you obviously know about the signs being positive or negative. So now let's take a look at some of the basic polynomial functions that we've talked about. We haven't looked at all of these before. We've looked at the first 3, that is, the very basic is y is equal to x. And remember, that's just a linear function, a line, through the origin with a slope of 1. Y is equal to x squared is our parabola through 0, 0, and 1, 1, and 2, 4. Y is equal to x cubed is that basic cubing function, right? It goes through the origin. That was an odd function. We had the point 1, 1, and negative 1, negative 1. Now, the others we haven't really talked about specifically, but you can graph these on the calculator, and I want you to notice the similarities that are occurring. When we get y is equal to x to the 4th, do you notice how its graph is looking very similar to the parabola? It's not called a parabola. It actually flattens out, so to speak, as we get closer and closer to the vertex. But do you notice how it's getting more narrow? And that's because the values of y are increasing much more fast, right? If I have the value of 2 when I plug in for x, 2 to the 4th power is 16, whereas 2 squared was just simply 4, right? But on this one we would have 216 on that graph. Now when we look at y is equal to x to the 5th, the same thing is happening. When we plug in values for x, the y values are growing much more fast. And also remember this fact for x, x cubed, and x to the 5th, when we put in a negative value for x, the outcome is also negative. So that's why we have values of the graph that are in the 3rd quadrant here, because a negative input is going to yield a negative output. Now when we put in x to the 6th into the calculator, we get a graph again that looks very similar to the previous 2 for x squared and x to the 4th, but again it's more narrow, and that's because if we put in 2, for instance, 2 to the 6th power is 64, so again it's growing very, very quickly. And another thing to notice is that for the power being even, when you put in a negative value for x, what is the output? Right, a negative raised to an even power is going to be positive. So some things to look at. Do you notice the graphs for x, x cubed, and x to the 5th? That is when the power is odd. You're going to have the domain being all reals, which that's definitely the case, but the range is also all reals. For even functions, what is the domain and range? Yeah, the domain of all of these is going to be negative infinity to infinity, right? The graphs extend indefinitely from the left to the right. But the range is what's different here. The range is just from 0 to infinity. And that is because of this fact that we talked about. What happens when you put a negative value for x, and what is the output? Let's see if we can notice some more similarities. Now we're going to look at graphs of negative f of x, where f of x is a basic function. So all those previous graphs that we just had, I've made the opposite. And if you remember what happens for negative f of x, we talked about this earlier, that negative f of x is really the reflection across the x-axis, right? And so look what happens when we have y is equal to negative x. That previous graph just flips over and becomes y is equal to negative x. This one is a graph of y is equal to negative x cubed, and y is equal to negative x to the fifth. And here we have y is equal to negative x squared, y is equal to negative x to the fourth, and y is equal to negative x to the sixth. So what is happening? Do you still see that the range, when it's odd, the range is still all real numbers, right? And whenever it is even, the range changes now. It is negative infinity to 0. So we talk about what happens at the ends of these functions, and it has to do with the power and the coefficient of that leading term. So let's go back to this graph for just a minute. When our powers are odd and the leading coefficient is positive, what happens for all of these functions? Right, it begins in the third quadrant and ends in the first. Right, so we talk about the end behavior being down and then up. It's down and then up. It's down and then up. What about if it's even and a positive coefficient? It is in the second quadrant and first quadrant, right? So it's up on the left and the right part of the graph. Now what about when we change that coefficient sign? So we still have odd powers, but now the coefficient is negative. Now it starts up and then ends down. So it starts up in the left direction and ends down. It starts up and then ends down. Whenever the power is even, but the coefficient is negative, still doing the same thing on each end, but it's all down. Okay? And that is what we call the end behavior of the graph. So the end behavior of a polynomial function depends on the degree and the leading coefficient. If the polynomial has an odd degree with a positive leading coefficient, it's going to have an end behavior that looks like this. Okay, think about the graph of x to the third for that one. If it's an odd degree with a negative leading coefficient, then that flips over, right? And that would become up and then down. So think about negative x to the third there. What about if it's an even degree with a positive leading coefficient? Well, then think about x squared. It's both up, right? Even degree with a negative leading coefficient. Well, then think about the reflection, which is both down. Think about negative x squared. So what we're saying here is that the graph of a polynomial function at the end, so as x gets very large or x gets very small, it's going to look very similar to these basic polynomial functions. So that's because as x gets really large, all those other terms in the polynomial don't really play that much into the output. In other words, the first term, that leading term, is what plays a major role in what the output is going to look like. So let's look at these polynomial functions. So I've given you some polynomial functions that look pretty complicated. But what we're to do is to be able to determine what the end behavior of these functions should look like by looking at the degree and the leading coefficient. And if we know the end behavior, then we should be able to match the function with the correct graph down here. Okay? So what we need to know, like in this function, negative 5x to the third plus x squared plus 3x minus 4, we know that this leading term has a power of 3, right? So we know the degree is 3. and the leading coefficient, I'm going to just call that LC, is -5. So here we have an odd degree with a negative leading coefficient. So based on what we just talked about, odd degree with a negative leading coefficient, it should look like that reflection of x cubed, right? So it should have an end behavior where it's up and then down. Well, which of those graphs begins up, right, or if you think about in the second quadrant, and ends in the fourth quadrant? Yeah, and that would be this graph right here. So we have one match right here. Now let's talk about this next one. 7x to the 6th minus x to the 5th plus 8x squared minus 8x plus 3. So this is a polynomial function, right? We have all positive powers on x. So the degree is what? Right, it's 6. It's the highest power. And the leading coefficient is 7. So here we have an even degree function with a positive leading coefficient. So in this case we think about x squared, which would look like this. It's up to the left and to the right. So which of these graphs has the end parts being both up? Right, well the only one would be this first one. So that must be the graph of this function. Now what about -4x to the 4th minus 13x cubed minus 8x squared minus 1? The degree of this function is 4, and the leading coefficient, right, it's -4. So here we have an even degree with a negative leading, so it's going to be the reflection of x squared, which will both be down. So the one that corresponds to that is here, right? The end behavior both going down. And our last one, 3x to the 5th minus x squared minus 8x plus 5. Our degree is 5. The leading coefficient is 3. So here we have an odd degree with a positive leading coefficient. So that's going to resemble x cubed, which looks like this. And here we see it's down to the left and up to the right. And so that would be the graph of that polynomial. Okay? Now notice that it does a lot of things in the middle, and that's something we're going to talk about. Here you're going to be able to use your calculator, so you're going to have to focus on finding those the right window to be able to view these graphs, and also finding these turning points that we call them. We're going to talk about that in just a minute. But I just want to get your feel for some things here. Like this function here has a degree of 5. Notice it crosses the axis 1, 2, 3 times. This function here has a degree of 4, and it crosses that 2 times. Degree of 6 crosses, really only touches 1 time. And a degree of 3 touches at 1 time. So we're going to talk about the number of times it can cross the x-axis. We're also going to talk about the number of times that the graph turns. You see turning, that means where it goes from increasing to decreasing, decreasing to increasing to decreasing, increasing, decreasing, increasing, decreasing. So that's going to play a role in what we talk about here. So let me go to the next slide and we'll talk further about those key things related to these graphs. And before we get into those specifically, let me give you some definitions. We talk about extrema and zeros. Zeros is a term we've seen before, so that should not be anything new to you. Extrema, we can talk about points on the graph where the graph changes from increasing to decreasing, or vice versa. There may be local extrema or absolute extrema. Local extrema are the highest and lowest points in an area. Absolute extrema are the highest or lowest points on the entire graph. And extrema are also called turning points. The zeros of a function are the values of x that make the function 0. Graphically, the zeros are the x-intercepts of the graph. Okay? So looking at this function here, we see that there are 1, 2, 3, 3 zeros. For this graph, we have 1, 2, 3, 4 zeros. How many turning points do we have? Here's a turning point and a turning point, or we can talk about extrema. There's 2 extrema. And these are what we call local extrema, because they're kind of a peak or valley, but they're not the highest or lowest point on the entire graph, but they are a peak or valley in an area of points. What about this graph? We have 1, 2, 3 turning points, or 3 extrema. Now one of them is an absolute, right? That is the lowest point on the entire graph. Okay, I'm sorry, I just got a phone call and I can't remember now where I was talking. This point is the absolute extrema. In fact, it's really called the absolute min because it is the lowest point on the entire graph. Now these are relative or local min or max. In fact, this is a local max and a local min. And back over here, this is a local max and a local min. Other things that we know about the graph, we know by the end behavior what type of polynomial this has to be. For this graph here, since the end behavior is both up, we know this has to be what? Do you remember? Yeah, think about x squared. It's an even degree with a positive leading coefficient. So if it's an even degree, this is a thing to note. If it has 4 zeros, it could be a degree 4, because you remember this fact that the degree tells you the number of solutions or the number of zeros to the function. For instance, a quadratic equation that is the power 2 has possibly 2 solutions, where that is 2 places where it crosses the x-axis, or it might only have 1, right, if the vertex happens to touch the x-axis, or it may not even have any. So we know it could be a degree 4. It could possibly be something higher, but it can't be anything lower. So the degree has to be at least a 4. And that's also true about the turning points. The degree 4 would mean that it could have at most 3 turning points, right? Because for it to hit all 4 of those, it has to go down below it, back up, then back down, and back up. So it can have at most 3 turning points. So this could be a degree 4 or 6 or something even, because it could be that those other zeros are real imaginary solutions. So that's why you could have an even power higher than 4 and still have it look like this. Now what about this function? What do we know about its end behavior? Its end behavior starts down and starts up. So which one does that look like on the ends? Yeah, x cubed, which tells us this has to be an odd function with an even, not even, positive rather, leading coefficient. Well, what do we know? It has 3 zeros, so here again it could be a cubic function because it would have exactly 3 zeros, or it could be a 5th degree. There could be 2 imaginary solutions that we don't see here. The other thing is that if it is a degree 3, it has to have at most 2 turning points, because if it had another turning point, it would come back down. So it has 2 extrema, or 2 turning points, 3 zeros. So this could be a degree 3, 5, 7, something odd. So here's an important fact. A polynomial function of degree n will have at most n real zeros, and at most n minus 1 turning points, or extrema, if you will. So this is saying if we have a degree of 4, then we could have at most 4 zeros, and at most 4 minus 1 or 3 turning points, okay? Just as an example. If we have a degree of 6, We can have at most 6 times where it crosses the axis, and at most 5 turning points. Okay, so the number of extrema is always 1 less than the degree. Now, it could be that you don't have that many turning points, okay? Just like in this previous slide where we looked at the degree and stuff. They didn't have as many of those turning points. In fact, this degree 5, it could have crossed the x-axis 5 times, but it didn't. It only crossed 3 times, and it only had 2 turning points. So keep in mind that word at most, right, or that phrase at most. It doesn't have to do that. It can do that many, but it can also do below that. So let me look at a problem now where you're going to be able to do this on your homework. But whenever you're given a problem in your homework and such here, you're not going to have to do this by hand. You're definitely going to use the calculator. So we want to identify key components of the graph of a polynomial function. That is, find the zeros, find the extrema, the y-intercept, domain, and range. We could do all of this on the calculator. So let me pull up the calculator here. So what I would need to do is go to y equals and input this function, negative 2x to the third minus 10x squared plus 6x minus 9. Now before I hit the graph, what do we know about this graph? The degree is 3 with a negative leading, so it should look like this, right, on the ends. It can cross the x-axis at most 3 times. So it has to have less than or equal to 3 zeros. And how many times can it turn? 3 minus 1, which is 2. So it could have at most 2 turning points. Now let's graph, and I'm going to graph in the standard window to see what we see here. Okay. Notice how it does that in behavior, but there's some pieces that we're missing. It's going down to a point, back up, and then turning again. So we need to refine our window. And it looks like we only need to refine it in the bottommost values, that is in the y values and the y min. So if we go to our window setting and change our y min, and right now I'm just going to guess, let's put in negative 50. If this doesn't work, then I'll go to the table. Our y max will keep the same, and maybe our scale is counting by 5s. And now let's look at the graph. Okay, I see it a little bit better, but I still am missing a little bit of the graph. So let's refine it a little bit. Let's go down to negative 100 and count by 10s. Okay, good. So that is the basic shape of the graph. So we see that it actually has just 1 0, but it does have 2 turning points. Well, I should back up. It has 3 zeros, but only one of them is real. The other 2 are imaginary. But you don't have to worry about how to find those at all. We're not going to talk about that in this course. But you do need to be able to calculate the zeros and the extrema, and we can do that on the calculator. So to calculate the zero, we've done that before. We do second and trace and 0. And remember, we have to do a left bound, so we have to be to the left side of that 0. You can do this with the arrow or enter in some number. So I'm on the left there. Now I have to be on the right side of that, which is here. Okay, and now our guess, we enter. Okay, so now notice this 1e to the negative 12. Remember scientific notation? That means 1 times 10 to the negative 12, which is 0.000000000, really 11 zeros, 1. So roughly that is 0. So don't let that freak you out. So the 0 is negative 5.67 if we round it. Okay. Now we need to find our extrema. That is, what are the ordered pairs of those turning points? Well, we've done that before too. We really find the minimum or maximum. So if we do second and trace, let's do the minimum point since I was closest to it. So here's our minimum point. We've got to be on the left side of it, which we are. And now on the right side of it, somewhere there, and then guess. I think I saw around -3. Okay. And now our minimum is -3.6, -66.9. Okay. So one of the local minimum, what was that? -3.6, 1, -66.89. And you'll be told how many decimal places to round those to. Now let's do our local max. So we do second, trace, our maximum, which is 4. We've got to be on the left side of it. So we are. And then the right side of it. And then we've got to guess. So it is 0.28 and -8.15. Okay, I'm going to forget this. 0.28, -8.15. Okay, now what about the y-intercept? Remember that if you press trace, well, I'm sorry, because we've been doing some stuff, I should have cleared that out. What we can do is type in 0 and enter. Generally, when you press trace, it automatically goes to the y-intercept, but if you've already been doing some moving along the curve, it's not going to do that. So our y-intercept is 0, -9. And then what about our domain and range? Well, for an odd degree function, or any polynomial function, the degree, or rather domain, is always all reals, so that's no question. The range, though, because of the end behavior, is also all reals. So the domain and range are all reals, or we can write -infinity to infinity. And that will always be true for an odd degree polynomial function. It's only the even degree that you have to worry about the range, because that's not all reals. Okay, but this is what you'll have to do in your homework. Be able to identify the end behavior, be able to identify the degree, the leading coefficient, be able to find these key things from the graphs. So if you have any questions on this, don't hesitate to contact me. Thanks.